Text is a convenient way to communicate and store knowledge. Many techniques are developed to process and understand text by computers. Text understanding include tasks such as sentiment analysis and customer profiling. To perform these tasks, text need to be represented in machine-readable forms, such as bag of words, a graph, a relational table, or a combination of them. In this paper, our focus is on information extraction techniques which create a relational representation of text. Extraction is a slow process. This graph reports the execution time for extracting some ordinary elements from DBLP dataset. The extraction time ranges from 8,400 seconds to more than 450,000 seconds. The poor execution time is mainly because extractors are evaluated over the complete text and scan every character in the document. On the other hand, source documents might be updated for legitimate reasons. For example, many records are added, removed, or modified in the DBLP database monthly. These changes need to be reflected in extracted bibliographic profiles. As a result, extractors need to be executed over and over, which makes the poor performance of the extraction process even worse. There are three main components in any extraction process: source documents, extraction algorithms, and extracted relations. Here is an example of extraction scenario. This document contains information about two publications belonging to James Allen. We are interested in similar queries to the one on the top. Here we like to extract key and title of articles that published in the Communications of HCM journal. As the result of this query, one record will be extracted. There are two important notions here. As you can see, offsets of associated values are being extracted. These intervals are called spans, and a table representing spans is called a span relation. In this work, we are dealing with extraction of span relations. An extractor can be an ad hoc program. It can be a machine learning model, or can be a set of rules based on regular expressions. In this work, we focus on rule-based extractors. This work is about how extraction happens rather than what elements are going to be extracted. This research is on properties of extraction programs that become critical when source documents or extracted relations are updated. Our main contribution is the important observation that we should treat extracted relations as materialized views on document databases. This implies source documents and extracted relations stay consistent all the time. This new perspective on extractors creates lots of opportunities to solve interesting problems that are mainly consequence of having updates on both ends. Today, I'm going to present our work on the optimization technique that we designed for information extraction process. This technique is applicable when updates occur frequently to source documents. By treating the extracted relations as materialized views, we develop a technique to avoid extraction from scratch as much as possible when frequent updates happen to source documents. We have developed our solution in a System-T-like environment. The main idea of System-T is to benefit from relational database concepts to deal with text data. System-T models each document as a single string and populates relational tables with spans directly extracted from the input document. Users write extractors with a language similar to SQL called AQL to work with tables or text. Users can use algebraic operators such as join, union, projection to manipulate tables. All these operators consider spans, not string values. Later on, the underlying principles of System-T have been formalized as document spanners by Fagan and his colleagues. We are interested in extractors that are expressed as document spanners. Document spanner is a function mapping strings to span relations. It can be any function, maybe a complex machine learning model, or a regular expression. Here we focus on the regular expression representation that has been used in System-T. Users write the definition of spanners similar to regular expressions, except that they can use some variables such as f, m, and d in this example to store the spans of matched regions. Then we transform the input regular expression to automaton that matches to the input string and produce the span relation. To make spanners more powerful, we add relational operators like union and join to the spanner specification. The semantics of relational operators on the specification is equivalent to applying operators to the span relations. In this example, on the left side, we have two regular expressions with capture variables that are joined with the shared variable f. This is the same as joining their corresponding span relations. Marciano has proposed efficient construction algorithms that construct automaton on top of the spanner specification, which directly simulates algebraic operators and produce the correct spanner at the end. For the update model, we follow the natural way of documents updates. Points of change in a document are expressed as a document spanner with one special exposed variable called update variable. The region marked by the update variable is replaced by replacement value. Replacement value can have back references to variables in the update spanner. In this example, update expression has three capture variables, f, m, and d. F is the update variable. M and D are back referenced in this replacement specification. The result of this update will be matching substring in a document that shows a particular way of writing date, then reordering month and day, and separating them with a slash and attaching 2023 to the end. We recognize three categories of updates: irrelevant, autonomously computable, and rest. Informally speaking, an update is irrelevant if applying extractor to an updated document and to the original document produces identical relations. Our research is on autonomously computable updates, which I will get into it in the next slides. We built a tool to determine autonomously computable updates. Our approach is based on static analysis of programs that is independent of the database size. The tool determines if the extracted relation can be kept consistent with the updated documents without running the extractor from scratch for all potential input documents in the database. Here is an example of autonomously computable updates. Two records are extracted applying the query on the top to the original document. And the update delete string http:// from all DOIs in DBLP dataset. This update matches and modifies two regions in this document. Since the length of text coming before the second extracted record has changed, the update will result in changes in the content of extracted relation. This example emphasizes that span relations contain pairs of offset, not a string value. Therefore, a span relation might be affected by an update even if the change does not happen within an extracted span. In fact, the updated relation in this example can be computed using a shift function. In general, if the updated relation can be computed using a shift function for all possible documents, the update is called a pseudo-irrelevant update. In this work, we studied pseudo-irrelevant update that is a special case of an autonomously computable update. Now I review some of the challenges that we faced in identifying pseudo-irrelevant updates. Some updates might not be well defined. Take the example on your left. It changes the order of month and day, but the update variable marks two overlapping regions. Therefore, after the update, the result is not correct. Or the example on the right shows a case that the region marked by the update variable has two different matches. So we have conflicting values for variables like m and d. To solve this problem, we have developed a polynomial algorithm that works on the update expression and determines whether an update is legitimate. Our proposed approach requires some conditions on documents that are the result of updates. To be able to model the post-update documents, we needed to apply further conditions on the update spanner. We developed a construction algorithm that uses the update expression and replacement specification to build a spanner that represents updated documents. AQL programs are usually complex and composed of regular expressions and various relational operators. We have shown that pseudo-irrelevancy of an update with respect to an extractor is closed under some operators. Therefore, in each program, we just verify the extraction expression. Even without changing an extracted value, an update could change the context that determines whether a span should be extracted. So if a document is updated, we want to know whether the extracted spans or contextual spans are disrupted. But the input expressions do not come with identified context. So part of our work was to capture the context automatically. We have designed a polynomial algorithm for this purpose. The last step was developing a verifier that can determine whether an update is pseudo-irrelevant. Our verifier can determine pseudo-irrelevancy in polynomial time. The essence of our verifier is to inspect various kinds of overlap between an update expression, replacement specification, and the extractor. We have two objectives when designing the experiments. First, through experimentation, we like to show practical update cases that can be expressed using our specification. Secondly, although our verification algorithm has polynomial time complexity, we are interested in showing that our optimization strategy takes much less time than re-extraction when we deal with practical extraction scenarios from real-world datasets. We have tried our approach on two different datasets. Here we report results for DBLP dataset, which has approximately 3 million documents with size of 7 gigabytes. We have designed queries with various selectivity and complexity, with low selectivity of 23 million records and high selectivity of 4,900 records. We have primitive queries that are expressed as regular expressions with capture variables, as well as compound queries that are built using algebraic operators on primitive queries. We have tried 4 updates. They modify various number of documents, ranging from 3 million documents to 20 documents. Our experiments show re-extraction required 14 hours on average, with a minimum of 2.3 hours to maximum of 43.4 hours, and with one of the compound extractors requiring more than 125 hours. Data shows that verification times are at most 3.5 minutes independent of the database size, and simply shifting extracted relations is far faster than re-extracting them, especially when the extractors are highly selective. In summary, outcome of experiments are very promising. We show that there are practical extractors and updates that are covered by our framework. Also, the whole verification takes much less time than extracting from scratch. Our approach to extracted mu maintenance will work for any extraction language that is based on regular expressions. The update model is compatible with systemd, and we have designed an efficient verifier for AQL programs. Our approach works on extraction programs expressed using core of AQL, but AQL is a broad language and has other relational operators, such as set minus and aggregation operators. We are planning to work on sufficient conditions for verifying a larger class of spanners, as well as necessary conditions for verifying some useful set of spanners.